Okay, our second concept today that we're going to discuss is the concept of Ksp, which applies to or refers to solubility equilibriums or solubility equilibria. So earlier in the year, we said that when something is insoluble, when it stays as a solid in solution, it does not dissolve. I know this is going in the picture section, but now we said when things are soluble, they do dissolve. Okay, now here's the new concept. When something is insoluble, technically a tiny bit probably does dissolve in the solution. And we are going to write that out like this. Let's say I had ionic compound AB, and our solubility rule said that this was a solid. Well, technically a little bit of this does dissolve into a solution. So this would be the dissolving reaction. Now the whole idea that we still have an equilibrium means that we have to have a reverse arrow also here. So now this forward process would represent dissolving, and at the same time we reach this equilibrium where the reverse process is also happening at the same rate. Remember, the rate of the forward equals the rate of the reverse at equilibrium. And we call the opposite of this recrystallizing. So in solution here, we're going to have A and B dissolving or dissociating into ions, and at the same time we're going to have these ions coming back together to form solid. When these two rates are happening at the same time, we say we're at equilibrium, and we have a K value for that. This is called Ksp for solubility product instead of just the other K earlier. Okay, now, because we're dealing with solids here, let's go back to our reaction here. AB solid. I know that could have easily been the notes too. Let's get the double arrow. We have A plus, and if it's dissolving, we need an aqueous there, and B minus, aqueous. So because we don't put solids in equilibrium expressions, the K value this time, Ksp, would just equal the concentration of the A plus ion raised to the coefficient times the concentration of the other ion raised to the coefficient. So I'm just going to say to the X and the Y. Now, since I have these brackets, this means this unit would be in molarity, and in this unit, when we say molarity, it often talks about like what is the solubility of it. So if it ever asks what is the solubility, it's looking for like this value right here. Okay, let's get down to the practice problems, and let me show you the type of stuff we're going to be answering this unit. So what occurs when a solid is first placed in a solvent? Well, at first the dissolving process will be the predominant process, but then the second that thing starts dissolving, it will also start recrystallizing as well. So you'll have kind of the forward and the reverse reactions both happening there. When do solutions reach dynamic equilibrium? What does dynamic mean? Dynamic means stuff is still happening. So this is when the rate of the dissolving equals, when the two rates are equal, so equals the rate of recrystallizing. Okay, how do we write a Ksp expression? Well, Ksp, we're not going to include solids in these Ksp expressions because solids don't have concentrations. So it would be the concentration of the calcium raised to its exponent, which looks like it's 1, times the concentration of the fluorine raised to its exponents. This would be F minus squared. Now also, I want us to think and take a second here. What would the concentrations of these two things always be? Think about the ratios. It will always be a 1 to 2 ratio. And I want us to be thinking about these mole ratios a lot here because it's going to impact both the numbers that go in here and the exponents they're raised to. Okay, now let's get to some sample calculations actually. It tells us copper 1 bromide, and again I'm being obnoxious here and making you remember that that is a +1 and this is a -1 bromine, which means its formula would be CuBr. Step 1, I want you to always write out the formulas and the reaction. It has a solubility of 2.0 times 10 to the negative 4th molar at 25 degrees Celsius. Again, that's just kind of throw you off a little bit. That might affect the solubilities, but we don't use that in calculations. It's asking in this problem to calculate Ksp. So first we should write out the substance. Next we should write out what happens. So it will dissolve into copper ions. And there's 1, so we have 1 there. And bromine ions. So once you write the reaction, I would then like you to set up the expression. So Ksp equals the concentration of Cu plus to the first power times the concentration of Br minus to the first power. Now this value here, it says has a solubility. So that means this solubility is 2.0 times 10 to the negative 4th molar, and this is a 1 to 1 to 1 ratio. So we are going to say then that Ksp equals 2 times 10 to the negative 4th molar times, and it's a 1 to 1 to 1 ratio, 2 times 10 to the negative 4th molar. So now on our calculators, we would go 2e minus 4 times 2e minus 4, and we get 4 times 10 to the negative 8th. So the first type of problem is when it says to calculate Ksp. Now what's the second type of problem? It's going to say calculate the solubility. This one is a little tricky, but we're going to practice. So let's look through this. Lead 2 chloride, and it gives us the Ksp value. So lead 2 chloride, again, I won't make you do the formulas later, but I'm just being annoying and making us practice here. Lead is a +2, chlorine's a -1. This is going to be key because we're going to have 2 chlorines in that molecule. This would be a solid. It will dissociate into Pb plus 2 ions, and we have 1 of those, and 2 chlorine ions, 2 Cl minus ions. Okay, we get a reverse reaction here. Okay, next, let's set up the Ksp expression. Ksp would equal the concentration of lead 2 ions raised to the first power times the concentration of Cl minus ions, and that would be squared because there's 2 of them there. Okay, now, this question gives us Ksp, and it wants to know these things. So here's what we're going to do. We are going to substitute this random variable or this random value x. So we have the Ksp, it's 1.2 times 10 to the negative 5th. Now, how many Pb's do we have in this balanced equation, Pb ions? We have 1 of them, so we're going to say that is x to the first. How many chlorines do we have? If Pb is x, what would Cl be? It's twice as many. It's 1 to 2, so this would be 2x. And then we have to square that also still. Okay, now we could simplify and say 1.2 times 10 to the negative 5th equals x times 2x squared equals 4x squared, in the parentheses, which equals 4x cubed. Okay, now to calculate the solubility, we just solve for x. So we would do 1.2 times 10 to the negative 5th, 1.2 e minus 5. Let's divide that by 4. And then to take the cubed root, on some calculators it's on here, but that would be also raising something to the 1/3. And I get 0.0144. And since it says what is the solubility, that unit would be in molar. And that's when it says calculate the solubility, you're solving for X here. Okay, I'm going to make a second video for the second practice 2 problems, and we can continue practicing setting up these KSP expressions, solving for KSP, and then solving for solubility, which is always X. Okay, I hope we got a good start. We'll practice some more, and then we'll read.